In this video, we're going to be writing and solving systems of equations from multiple representations. By the end, you should be able to solve a systems of equations using substitutions when given a graph, table, or real-world problem. Remember, to write an equation from a graph or from a table, you're going to need two things. You're going to need the slope, and you're going to need the y-intercept. The slope is the change in y over change in x. So from a graph, you could look at rise over run. And from a table, you just simply look at the changes in the y's and the changes in the x between 2 points. To find the y-intercept, it's when x is 0. So that's on a graph, that's where it crosses the y-axis. If you can't clearly see the y-intercept, or if the 0 is not given to you in the table, then you're going to want to use point-slope form in order to get the y-intercept. Remember, when we are writing systems of equations from word problems, remember that our two types of equations that we commonly see are slope-intercept form and standard form. Slope-intercept form will have a rate of change and a beginning amount, which would be your y-intercept. Standard form will lay out those two variables for you pretty explicitly, and it'll have two totals for you to be able to draw from. One of the word problems that we're going to be looking at today is going to be distance, rate, and time problems. The important things here to know has to do with the directions, and that's going to help us, or the distances, which is going to help us set up equations to find the time. When they're going in opposite directions, when you have objects going in opposite directions, to get the total distance, you would need to add or combine the distances of both objects. When the objects are going in the same direction, or it's a round trip, we know that those distances are equal, and so you'll be able to set the equations equal to each other and solve for the variables using substitution. We're going to be using a distance, rate, and time table. This is going to help us to clearly set up our two equations and get them written properly. Okay, so number 1 says use the graph and table to write two equations. So from writing the equation for the table, notice that all of the y values are the same. So this would be an equation, or this would be a situation that has 0 slope, as the change in y would be 0 over the change in x, which would be 1. Anytime that we see this, we know that 0 slope is horizontal, and it's going to be a y equals equation. It's just going to be y equals whatever those y values are. So we know that y is equal to 3. So that is this equation. For my graph, I just need the slope. So change in y over change in x. So that would be negative 2 over 1. So my slope for this one is negative 2x. And we see that it crosses the y-axis at 5. So negative 2x plus 5. So here are my two equations. I can solve them using substitution. Remember that when two things are equal to the same thing, such as y is equal to 3 and y is equal to negative 2x plus 5, that means that they're equal to each other. So I can set 3 equal to negative 2x plus 5, and I can solve it. So I'd start by subtracting 5 on both sides. I get negative 2x equals negative 2, divide by negative 2, divide by negative 2, and I get x is equal to positive 1. So I know that x is 1, and we already know the y value. The y value was 3, so my point is 1, 3. Looking at this one, we're doing the same thing, so I'm going to write the equation from each table, or from the table and for the graph. My change in y from my table was negative 3. My change in x was positive 1. So my equation starts out as negative 3x, as my slope is negative 3. My y-intercept is positive 1. So my equation for my table is y equals negative 3x plus 1. For the graph, we have y equals, my slope is 2 over 1. So that's positive 2x. My y-intercept is 3. so that would be 2x plus 3. I have my two equations here. I'm going to set them equal to each other because they're both equal. They're both in slope-intercept form. So what I can do is have negative 3x plus 1 be equal to 2x plus 3, and I can solve. So plus 3x, this would be 1 is equal to 5x plus 3, minus 3, minus 3, I get negative 2 is equal to 5x, so x is equal to negative 2/5. We want to leave our answer as a fraction unless the problem calls for a decimal. Fractions are a little bit more accurate, so we want to leave them as fractions, and it will actually make our life a little bit easier when we solve it. I take x, whatever x is equal to, so I take that 2/5, that negative 2/5, I plug it into one of the two equations. So I'm going to plug it into the second one. So y equals 2 times negative 2/5 plus 3. Y equals negative 4/5 plus, and I can't add 3 to the fraction, so I'm going to change 3, which is 3 over 1, so that it has a common denominator. 5 would be the common denominator, so this would be 15 over 5. And then y equals, well, negative 4 plus 15 is 11 over 5. And so my x is negative 2/5. My y is 11/5. And it's okay to have fractions. Looking at 3, it says Jane invests $9,885 into 2 accounts. A savings account earns 6% interest, while a money market account earns 9.5% interest. After 1 year, she made $696.35 interest from both accounts. How much did she invest into each account? So these are going to be both written in standard form. X is going to represent the amount invested into savings, and y will represent the amount invested into the money market account. Okay, so my two equations here are going to be x plus y is equal to $9,885. And my second equation will represent the interest. So this would be 0.06x plus 0.095y. I changed those percents to decimals. And that's 696.35. So those are my two equations. Now, I'm solving this using substitution, and so I'm going to have to change one of the two equations to solve for one of the variables. So I'm going to solve the top equation, and I'm going to solve the top equation for x, because when I plug it into the second equation, it's going to be easier to multiply everything by 0.06 than it is to multiply everything by 0.095. So I want to change the x so that I can plug it into that. So x plus y equals 9,885. When I solve it for x, it would be x equals 9,885 minus y. So there is my new equation that I'm going to use to substitute in. So I'm going to take, instead of 0.06x, now I'm going to have 0.06 times 9,885 minus y plus 0.095y is equal to 696.35. I take 0.06 and I multiply it to 9,885, and I get 593.1 minus 0.06y plus 0.95y, or 0.95y equals 696.35. I combine like terms here, so if I combine negative 0.06 plus 0.095, what I'm going to end up with is positive 0.035y equals 696.35. 0.35. I subtract 593 from both sides. Again, we're solving for y, so I need to get everything away from that. So subtract 593 from both sides. What we have is 0.035y equals 6 minus 5 is 1, 9 minus 9 is 0, 6 minus 3 is 3, 3 minus 1 is 2, 5 minus 0 is 5, so we have 103.25. Last step is to divide by the coefficient, which in this case is 0.035. When I do my calculations here, what we end up with is 2,950. So that's the amount that's invested into the money market. I need to take this and I need to plug it into one of the equations. So I'm going to come back up here and I'm going to plug it into this one because I know why. So all I have to do is take 9885 and subtract 2950 from that. And what I end up with is x equaling 6,935. Again, the 2,950 represents the amount invested into the money market. Let me switch that. Okay, and the 6,935 represents the amount of money that was invested into the savings account. And you always want to make sure that you go back and you write out your solution in words. Okay, here's the first of our two distance, rate, and time problems. We're going to use the table to kind of help us gather the information that we know so that we can write our two equations and solve. So we have a train leaves the station at 2 p.m. It travels at an average rate of 60 miles per hour. So I know that train 1 has an average rate of 60 miles per hour. A high-speed train leaves the same station an hour later on a parallel track. It travels at an average rate of 96 miles per hour. How long does it take for the second train to catch up with the first one? Well, I know they're traveling the same distance because train 2 catches up with train 1. T represents time in this case, but the time for both trains cannot be the same because train 2 left an hour later and reached the same destination at the same time. So train 2 is traveling a little bit faster. So we're going to make T the time it takes for train 1. So time for train 1 should be T. And we're going to use that to help us figure out the time for train 2. Well, if I know that train 2 left an hour later and it gets to the same destination, then it should get there. It should take an hour less time. So if train 1 left at 2 p.m. and it arrived at the station at 4 p.m., then that means that it took it 2 hours to get there. So if train 2 left an hour later, then it only took it an hour. So it took train 2 an hour less time to get there. So I take the time for train 1 and I subtract it by 1. And so that will give me the time for train 2. Once I have this information, I can begin to write my two equations. So my first equation is going to be 60 times t, so r times t, and that's going to be equal to the distance. My second equation is going to be 96 times t minus 1, so times what's in this column, is equal to d. And so there are my two equations that I can set up and I can solve in order to be able to answer the question. So we would have 60t is equal to 96t minus 96. If I subtract 96t from both sides, what I end up with is negative 36t is equal to negative 96. Divide that on both sides. Divide negative 36 on both sides. What we end up with is t is equal to 8 over 3, which is not super helpful for us. So that would be 2 2/3. So 2 hours and 2/3 of an hour, which would be 2 hours and 40 minutes. So if I take 2/3 of 60, 2/3 of 60 is 40. This is the time it takes for train 1 to get there. So train 2 will get there in 1 hour and 40 minutes. That's how long it will take train 2 to catch up. If we look at this last one, it says Noya drives into the city to buy a software program. Because of traffic conditions, she averages only 15 miles per hour there. On her way home, she averages 35. We know their distances are the same here because it's round trip. So their times can't be the same. So again, I'm going to make the time to get to the store t. So I'm going to need to use the information to get, I'm going to need the rest of the information to get the time to get back home. So if I know that time to get to the store is t, we also know that the total travel time is 2 hours. So I know that the time to get to the store plus the time to get back to the store, or to get back from the store, is 2 hours. So if I want to figure out just the time it took to get back to the store, I would take the 2 hour total time and I would subtract the time it took to get to the store. So I would take away t. So my second equation would be, or my second time to get the time to get back home would be 2 minus t. When I'm writing out my two equations here, my first equation would be 15 times t equals d. My second equation would be 35 times 2 minus t equals d. So if I set these two equal to each other, we have 15t equals 35 equals 2 minus t. 15t equals 70 minus 35t. Add 35t to both sides. 50t equals 70. T is equal to 7/5, or t is equal to 1 2/5. Again, 2/5 of an hour would be 1 hour and 24 minutes. So the fifth of an hour would be 12. So 2/5 would be 24. And that is the time it took for her to go to the store. So the time it took for her to drive to the computer store was 1 hour and 24 minutes. Before watching the next video, what I would like for you to consider is how we write an equation from a table or a graph.